So now in this video we're going to look at our first example for this video series of more than one logic gate being combined together to make a different logic gate. So what we have over here for the circuit is ultimately a buffer circuit, a digital buffer. So we have a low input right now, a low output. The blue LED is lit up because of the way I wired it. Now we have a high input. The LED is lit up because the output is high. So we actually got a couple outputs. This is a couple NOT gates that are connected in series. And the big reason why I'm doing this, I don't have a buffer integrated circuit that will work like this, at least not in the 74 high-speed CMOS series. So in any case, we get a high enough voltage in. That gives us a low output. But that output is the input for the other inverter. So low in, you got high out right there. And when you have a high out, that's like 5 volts coming out. Actually, you lose about a volt. But in any case, you got maybe 4 volts coming out and then going through the red LED because it heads to ground. Now, if you drop the trim pot down to a low, again, it's inverted to high, but that output is the input of another inverter. So high in, low out right there. And that's when the blue LED will light up. The output goes to ground. Probably connects pretty well. So this is an old diagram. I added the 74HC14 specs from a data sheet that I got. And so yeah, you can power these with like 2 to 5 volts, 2 to 6 volts. I mean, you have an output limit of about 25 milliamps, either sinking or sourcing, whatever direction. But you limit the total current of the integrated circuit to about 50 milliamps right there. And they recommend not to leave the inputs floating. So you'll see wherever there is an A, because there's only one input with NOT gates, so there's no B or C or whatever. So wherever you see A, I put a jumper. Since I have a bunch of yellows, I'm using them to indicate positive, a direct positive connection to those inputs there. So hopefully that makes sense. But in any case, we covered all of this really before. I will mention again, we have the Schmitt trigger effect, so that there is no middle ground region. If I turn the trim pot, if I try to set it halfway, it doesn't like fluctuate back and forth or have a, I'm not sure what it is, zone. There's a middle ground region where the output stays in whatever state it was last put into. That's hysteresis. So it could be either state right in the middle, but if you go more extreme one direction or the other, that is a solid input, either high or low. So, in any case, going to keep this short. This is the short video series. Hope you enjoyed.